So let's continue. Well, good afternoon to all of you. We're very happy to welcome you in Lyon for this seminar on optics and ultrasound. I will be continuing this nice presentation by Karin to see how these things are being used in ultrasound. So there will be some overlap with the presentation said by Stéphane, by my colleague Stéphane, and but we'll be seeing slightly different ways and actually slightly different focus in this talk. We're talking about speckle tracking. We'll be talking about the details, how we do the speckle tracking in ultrasound. And it was actually funny listening to Karin that I'm looking at all the efforts being made to create speckle in the world of optics. Whereas in ultrasound, there's quite a bunch of papers and groups that have been working on reducing or removing speckle because we don't like it. But anyway, that's just a fancy note. The reason why we're talking about elastography and why elastography becomes so important in medical imaging is that there is obviously a need for physicians to detect pathologies that are highly associated with stiffening. You can know, all of you can think of breast cancer, prostate cancer is also the case, thyroid cancer, or these are all focal diseases that are associated with local stiffening. But there are also diffuse diseases. Diffuse means it progresses through the whole organ. And this is the case, for example, fibrosis or cirrhosis in the liver, where the whole liver, or maybe a major part of the liver, can be affected by cirrhosis or fibrosis and get stiffer. And that's actually why the medical doctors exert palpation on the liver to feel the stiffness, and it can tell basically how much you've drank. Not all these techniques are basically subjective and not quantitative, so there's been an urgent need to develop techniques. So it's been done over the last 25 years or so. And today, the reason why we make the elastography so big in this seminar is that it's becoming commercially available to all medical doctors, and even not to all labs, through all major manufacturers now offer some kind of ultrasound elastography in their scanner. But we'll be seeing that all these scanners just cover different techniques, actually. The two major techniques being strain imaging, and you see some strain image from Karin. But we also have additional images that go into quantitative elasticity imaging, and whereas strain imaging will only be a relative measurement of stiffness, the shear wave imaging will provide us with quantitative. So what's the difference? If we get started with strain imaging, first well, most of you would know, but for those of you who are new to mechanics, what is strain? Strain is very basic. You can see it as the percentage deformation of a material under some load or under some effort. And so this bar, for example, had some initial size. I squeeze it by so much, so it has a new size and I measure the difference. It has a 10% change in size, that's the strain. And if I squeeze it harder, you get 20 and 30% strain. So that's really the percentage deformation that we're looking at. And this strain tells us something about stiffness. Because if you think of this, for example, it's a sandwich, it's a 3-layer sandwich. And yeah, it's made of 2 stiff layers and the softer layer inside. And assume now I compress on the top of the sandwich using a rigid plate. The whole thing is going to squeeze, but we'll get different deformation in all the layers, obviously. You can guess intuitively, but the stiff layers will undergo little deformation, so little strain, whereas the soft layer will undergo high deformation. And this is actually what you're seeing in this part of the image, with the stiff layers having roughly the same size. Actually, in this scenario, it's only been deformed by 10%, whereas the softer layer has been squeezed hard and has been actually squeezed by 30% in this hypothetical scenario. What strain imaging will provide is actually a strain image of the person deformation within each layer, and will actually look like that, where strain here is encoded as brightness. So you get white in this scenario being high strain, so it's typically softer, and dark being low strain, so it's typically stiffer. And still you can see that if we can get a strain image, then we get some information about the stiffness contrast within the medium. This example was actually one of the very first strain image by ultrasound in the literature. It was back in 1991 in a seminal paper from Professor Shear, where he actually made this experiment, and he was having this 3-layered phantom, and he was imaging this from the top using an ultrasound probe that's put on the top where the blue arrow is here, and using this ultrasound scanner he could get an ultrasound image which we call the sonogram, that you can see on the left hand side of the screen here, and see there's some, well, there's some contrast. You can guess that maybe there's something different in the middle, but it's not that good and not that clear what the layer is and what the contrast is. But by producing a strain image, and I'll get back to how we produce the strain image a bit later, we can easily and very clearly see the 3 different layers, the 2 stiff layers that undergo low strain and the soft central layer. So that's an experimental image and one of the first earliest strain images in the field. One thing to care about when we're interested by the elastic or mechanical properties of the medium is that strain tells us about stiffness, but strain is not stiffness. And just to demonstrate that, I've just been using this very same phantom. I'll be rotating it on its side. So now the 3 layers are vertical, and I will perform the same experiment. I will just put my plate on top of that, compress, and determine the strain in all 3 layers. So what happens? You can see that all 3 layers get actually deformed by the same amount now. So they all undergo 10% strain. And if I make this a strain image, you see that the strain image is totally uniform and totally uninformative. It's the same medium, it's the same technique. I've simply rotated the phantom, and it's become totally useless. And so what's happened here is that in these strain image techniques, we do not account for stress. We actually do not see stress. And what has actually changed here is that the stress has changed within the 3 layers, and with the 2 stiff pillars, they actually act as 2 columns, like in Roman architecture, and they actually stand all the weight. And so there's larger stress in there, whereas the central layer actually undergoes very little stress. But the point is, with ultrasound, we do not see stress, so we do not see what happens. All we see is the strain. So this is to show you that it will be very easy to make a strain image, but interpretation of the strain image is prone to errors and takes careful attention what is going on, and especially with this stress that may or may not be applied depending on boundary conditions. So how do we get the strain image? That's how we get into the Speckle Tracking algorithm. You've heard a lot about the Speckle Tracking. Some of you may already have used some about ours and developed some. But for those of you who are new to the field, strain tracking is simply following this speckle. What we call this speckle is this specular aspect, this dot aspect that you can see in all ultrasound image. It's actually based to the nature of the ultrasound image, to the echo formation. And you've seen that in the this morning with the ultrasound techniques that we use. The speckle is actually an inherent property of the ultrasound image that we get, meaning that even a uniform medium will show some speckle. And this speckle shows up as bright or dark dots in the image. And what we do with speckle tracking is actually tracking all of these motions. This is the same example with the layered phantom. And I've now represented some particles within that phantom as some dots so that you can see them by the eye. And I've largely exaggerated the motion so that you can also see them by the eye. So you can look at some particle, choose the one you like best, and just you can, by the eye, follow the motion, frame after frame. And this is exactly what our algorithms are doing. It's not unique to ultrasound. Everybody knows that. It's a basic, it can be a very basic image analysis process. And you could use even some very conventional tools like optical flow or others to do that. But we'll see that in ultrasound we have additional information. We don't only have the image, we have the underlying information, that is the signal. And that will allow us to go to much better resolution and detection. But just to put the numbers there, if you just try to follow or track the speckle in the raw body image, that's a sonogram that you get on the screen of your scanner, you can expect an accuracy of about, say, 0.5 millimeter or 0.1 maybe, as a word, in the millimeter or sub-millimeter range. But now we'll be using the ultrasound signals, and I'll get back to that later. And with using the ultrasound signals, we will get the resolution down to micrometer. And we can, that's the scale we're looking at when looking at ultrasound elastography, whether it's strain or shear wave. We're looking down at the scale of micrometer or even sub-micrometer motion detection. So it's extremely sensitive, and it can be done with a conventional medical probe. So just to show you how it's going here, there was actually, for those of you who didn't see it, there was some hard inclusion in this previous example, and here it's represented in red to help you see it. So I keep squeezing here, and if I imagine tracking all of these particles and create a displacement map showing the value of the displacement for each particle, because displacement changes in time, I will end up with a displacement moving. That will actually look like this. So this is done by the motion tracking algorithm, and you see that we get a displacement map that shows displacement at different times for each pixel within the image. And once you get that information, remember that what we want is strain. Well, strain is simply the spatial derivative of displacement. So by taking the gradient of this displacement field, we end up creating the strain image that we're after. And that will actually be a dynamic image. It used to be called static elastography because in the lab condition it was just performed with the first pre-compressed image and the second pre-compressed image. But in current ultrasound scanners, it's real time and it's showing the strain that you're actually performing. So if you don't move, you don't apply any strain. Strain is 0 and you've got a black image. But if you move just a slightly bit, and we're talking about just percent deformation, just a fraction of millimeter, you don't have to squeeze hard, then you get these images, and you see that they're dynamic, actually showing that the strain at some instant is more or less pronounced or more or less intense, and you actually get to see not only the inclusion here, but also you can get some artifacts such as stress concentration that you see. You see this white area here. It's not softer. So what's happening here, it's again one of the pitfalls of strain imaging. Remember that strain is not elasticity. And what happens is, because we have this very stiff ball here, it's not going to deform much. So all the surrounding soft media, has to undergo quite a harder deformation because it's squeezed between the top rigid plate and this hard ball that doesn't want to compress either. And so this is why we get this strain concentration. So you've understood that strain is probably easy to see and to pick, but it's not optimal if we want to reproduce the exam. Say I want to scan a patient who has some suspicious nodule, and I get some strain image. I say, oh, it seems to be stiffer, and see how this thing evolves. I'm not sure what it is. See how this thing is going to evolve in the future, and come back in 2 months and we'll scan it again. Then I'm in trouble, because in 2 months it's likely that I'm not going to reproduce with exactly the same amount of compression. I'll get a different image and I won't be able to compare. And that's the reason why having quantitative shear wave imaging is so desirable. And this quantitative aspect is what we're going to get with the shear wave imaging techniques. So shear wave imaging techniques, we want to quantify elasticity, so we need to get back to the basics and see how in mechanics elasticity is being quantified. Elasticity is quantified by a bunch of modulus. They call modulus, which are actually a ratio of stress and strain we've been talking about till now. And depending on the test being performed, you can define quite a lot of moduli. And the two major moduli being, for an elastic medium, the bulk modulus, is related to compression. It's how a material resists compression, a change in volume. So this is why it's squeezed by all directions in this example, and it will resist with to exert some resistance to a change in volume. But I can also try a different test where I will now shear this material, and this is the image on the bottom right-hand side of this slide here, where now the same cube is being sheared by applying gradient forces on both sides. So now I've got a totally different deformation. When doing the compression experiment, I was actually not changing the shape of the material, I was only changing its volume. Now it's the total opposite. I'm changing the shape without changing the volume. And this material exerts some resistance to that new deformation as well. But the resistance is not the same. It's not the modulus. And in most materials that we are interested in medical imaging, it's actually much softer. And this is actually the modulus that we actually feel with palpation. And one of the typical experiments in mechanics is to compress medium between two plates. And what you actually get here is an estimation of the Young's modulus. For the purist, you will probably need to have a cylindrical sample here, but that's just to keep the shape and make it cubic. What happens in this experiment is that you apply uniaxial compression, but because the medium is at least partly uncompressible, it will undergo expansion on the side. And so you see what is happening here. We will have simultaneous change in volume and change in the shape. So both moduli, bulk and shear, are involved, and they actually combine into what is called the Young's modulus. The two latest cases are the ones who are interested in medical imaging, because they are the ones related to palpation. If you look at the bulk modulus, it's how it resists compression. Remember that ultrasound is compression waves. And in ultrasound imaging, we assume speed of sound is the same everywhere in the body. That's how we can make the image and convert from time of flight to distance. And it's actually quite a lucky coincidence that the bulk modulus is basically the same for most tissues, or roughly the same for most tissues. And this is what makes speed of sound roughly the same for most tissues, and that's why ultrasound scanners work. So bottom line is, if you look at bulk modulus, there's no contrast in that. You could see it in Stefan's slide with the inclusion. There was probably some junk. But now when looking at palpation, we're interested in the other moduli, in the Shear and Young's moduli. And now, how do we measure these moduli? We will be using waves to feel these moduli at a distance. Let's first about the difference between OCT and the technique shown previously. OCT can look down at depth, whereas the previous technique with its two cameras inside could only look at the surface, with the advantage of having a very simple device. Now, in the case of ultrasound, close to the case of SCT, we'll be looking inside the matter, and to look inside, we will be sending waves to probe the properties of the matter. We can send pressure waves. That's what we do when we're doing ultrasound. So just to, as a quick reminder, just showing an illustration, with a pressure wave here, you have a piston on the right here that gives some initial impulse on this material. And that's made of some particles again, and you can see the motion of the particles under the initial impulse. They're going to vibrate, and they'll be shaken, they'll move, but then they will move back to their initial position. However, even though each particle moves a bit and comes back to the initial position, the perturbation gets propagated from one side to the other. And so we see we have two different dynamics. One is particle velocity, and the other is the sound velocity of sound, because what we're looking at is actually the sound wave. It's actually the same in ultrasound, or same sound wave I'm using now to talk to you. The particular aspect of these pressure waves is that the particle vibration and the propagation of the perturbation are collinear. They're all horizontal in this case, and we speak of longitudinal waves. Now shear waves are different. Shear waves are a bit different. Now we're going to shake this same material up and down on one side. And it's like shaking a rope up and down. And what happens is that the initial perturbation is vertical. But as you can see, it will propagate horizontally. And so we have now perpendicular vectors between displacement and perturbation. And this is why we also call these waves transverse waves. The reason we're interested in shear waves is that their propagation speed depends on the shear modulus. So if we can get to see the shear waves and see how fast it propagates, then it's possible to measure the shear modulus. So how's that? Well, if we take a very simple model, it's actually the simplest mechanical model that you can take. It has no viscosity, it's just an elastic model. It says that the shear modulus is equal to the density multiplied by square wave velocity. And in that case, in the case of medical imaging, density is more or less the same within a few percent for all organs. So if we assume that we know density, it's about the density of water, you can see that all we're left is wave velocity, meaning that if we get a way to see or measure wave velocity, then we're done. We can create a shear modulus image, which is what we're after in quantitative elasticity imaging. There are various ways to see wave velocity. To see wave velocity, you need waves. You could either use transient wave, and that was the previous slide where we just pitch to propagate. And in that case, you have a movie where you can try the wave at different times. You know the distance, you can measure the distance, you can measure the time, so you can measure the velocity from that simple movie. And so, as we have velocity, we can have shear modulus. But now we can also use continuous vibration. In the case of continuous vibration, we set the frequency of the vibration. We use a vibrator with sub-frequency, and this is actually what we do in MRI typically. And then we can see the total wave field, and from that wave field you see we'll show up some wavelengths, and the wavelengths will be related to the velocity by a simple and well-known relation, say that actually velocity is the wavelengths multiplied by frequency. I'm sorry. Because I can measure the wavelengths from the image, I know the dimension, I can measure it. The frequency is something that I've set. So I know these two parameters and I know the wave velocity, so now I'm done again. I know the shear modulus. I can make a shear modulus out of that. And this is how MRI elastography works, except with the new techniques that we're using at Laptop. And now, shear wave imaging with ultrasound, you'll see that in most cases you can just use a simple push. What we'll be doing is just creating some transient shear wave here in the middle of the field of view using radiation force of whatever vibrator you can think of. And if I press in the center of this region, I will have two shear waves diverging on both sides. And you can actually see them by the eye again. I've also largely exaggerated the motion. In typical experiments, it's only about 10 microns or less than 10 microns. But here, just for the sake of clarity, and so that you can see it and do speckle tracking by your eye, it's largely exaggerated. We will now be using the exact same speckle tracking algorithm that we've used for strain imaging. What was true for strain imaging is also true here. We're after motion. We're tracking motion. So we've got these are ultrasound image with some speckle. We will be applying our speckle tracking algorithm. And again, we will get a displacement image. Except that now it's going to be dynamic and different. And we will actually see displacement as the initial push to the center, and then it propagates at different distances. And if you look carefully, you will see that they initially propagate the same speed, but then there's some change in propagation speed. And now you're aware that this is exactly what we're after. We're after all these changes in propagation speed. So but it's clearly not easy to see in this image. So there is a second tracking step where we're going to track the shear wave from the central position to every pixel and see and measure how long it takes to get to every pixel. And for measuring distance and time again, we will be able to reconstruct now through the wave tracking speed, a wave speed image. And this wave speed image in this example will look like this. You see there were actually 3 different materials in this image, so 3 different speeds, central being some medium stiffness, and a very soft medium on the right-hand side, and a stiff one on the left-hand side. And now the new thing compared to strain imaging is that we have a quantitative scale. It scales in meters per second, because this is the wave velocity. And we can convert that to shear modulus if we want to. So these are major differences between the 2 techniques, and this technique has another advantage. You see, we're not hindered by the boundary condition. In this example, for example, the 3 layers are vertical. That was the scenario that was causing problem to the strain image. You see, it's not creating any problem to the shear wave technique. We can retrieve the 3 regions without any artifact. And just because we're in engineering and you like to know what's behind the scene, I'll talk more about the speckle tracking, how we do that. I was saying that we're going to use the signals and not merely looking at the image. And the way we do speckle tracking in ultrasound is based on the principle of A-mode pulse echo. So I assume you've seen that corresponding with the basics of ultrasound imaging. In A-mode pulse echo, you assume you have some ultrasonic transducer. That's this blue ellipse here. That will act as both a transmitter of a compression wave and also for the reception. So initially, to do the ultrasound image, to transmit some ultrasound pulse. So it's a pressure wave, and it's going to travel over distance, and it will meet some obstacles. And when it meets obstacles, part of the energy of the pressure wave will be reflected back to one transducer. So if we look at the pulse, after a few moments, it's traveling, but it has not reached the obstacle yet. So I'm looking now a moment afterward. This pulse has reached the obstacle, but what do I see on my scanner? I see nothing. You look at this blue line here at the bottom. This is the voltage on the transducer on the airline. So I'm now using my ultrasound transducer here as a receptor, and the voltage on it, so it's converting pressure waves to electricity and to voltage so that I can measure it. Because I have not received any echo yet, the voltage is actually still 0. I am not measuring, the wave has not come back. So I'll wait a bit more. What happens next is that most of the energy continues its way towards the distance. The part of the fraction of the energy was reflected back. I need some way back, but I don't know it. I still have not measured it. And if I keep waiting, it keeps propagating. I actually get a second echo from the second obstacle there, and I have the transmitted wave that continues its way over till it dies. And then after some time, the first echo actually reaches my ultrasound receiver. So I measure some voltage, and I can see this first obstacle. So this is down to the very basics of ultrasound imaging. It's just listening to these echoes. And after some time, if I wait a bit longer, I will be receiving the echo from the second obstacle. So I get these 2 echoes on my line. And because we assume we know speed of sound, and we can convert the time, we know the time of arrival. We just measure the time because what we're listening to is signal as a function of time. And we can convert this time of arrival to distances. We simply know that time of arrival is twice the distance divided by speed of sound, a factor of 2, simply accounting for the round trip travel because the pulse have to propagate twice. Okay, so you've seen it all this morning, so how do I get that to get a displacement estimation where after it's very easy? Say I assume I only have one obstacle, so now you know the principle. I get the echo from this obstacle, and it's reaching a distance d1 initially, it comes back at time t1. Then for some reason there is some motion in the tissue, it will move back, it will move to some new distance d2, which is this one, d1 plus d, it's one displacement. Then the echo, I perform a second ultrasound image, so I get a new echo from the same obstacle, but it's moved, so the time of arrival has changed, and it's now related to the new position. Now if I compare the two signals, I can measure the time delay between these two echoes, and this time delay to, if you do the math, there are the slides that pretty less straightforward. They're directly related to the distance, so I can measure this delay tau from my signals, because I get two signals as a function of time. Just by measuring the delay between two signals, I can measure tau, and then knowing tau, I can convert to distance by multiplying by c divided by 2, as we do in ultrasound. So I know the distance for that specific obstacle. And finally, to leave that last slide, anyone who has practiced ultrasound will say it's a very simplistic explanation, because I never get just one obstacle that I can easily identify, get some weird speckle pattern, and how do I know, how do I recognize my obstacle, my pattern? And the answer is, as Stefan was saying, we just pick a window, and actually you can think of medical or biomedical imaging, especially medical organs, as being millions of small echoes, like from the cells, from all structures down to very small sizes. So we get millions of these small echoes within one resolution cell. And they actually create a signal by some either constructive or destructive interference that create this randomness in the signal. If you look at the true ultrasound signal, it will more or less look like the signals that we have here, with, you'll see some central frequency, that is the central frequency of the transducer, but you will see some varying amplitude depending on whether the interferences were ended up being constructive or destructive. So that's how we recognize the signal, by picking a window that is long enough, and that is a trade-off here. By taking a window that's long enough, you can recognize some signature, and that you can search, you use search on the next signal for this same window, and actually measure a new time delay here, but it's not exactly between individual obstacles, but between a group of obstacles. That is some matter. And this is how we can perform for each pixel the tracking in the ultrasound image. And that will finish the presentation for these techniques for today.
I have a question about the last slide. Do you use B-mode image or RF?
These are the ultrasound signals, so we always use the RF data. And the reason is we get so micron precision with RF, whereas with the B-mode it will be in the millimeter range.
And the second question is, if there is compression, the second signal is also compressed.
Yes.
Do you compensate for that? Or?
Some algorithm compensates for that, and it actually improves the tracking. So it's recommended to use this compression. Some algorithms use multi-step with the first cost estimation, and then apply first compression so that the signals are more thin, more alike, and we're improving correlation by making them the same way. So depending on the amount of deformation, it may be advisable to use some compression. Some of these algorithms have been developed.
Okay, one last question. Go ahead.
How crucial are displacements that have a component perpendicular to the imaging?
That's a very good question. And because I've oversimplified for the sake of time and simplicity here, the displacement is actually 3D vector. It's not just a scalar as in this slide. So as we get 3D displacement, we also get lateral displacement that will go actually from one of these A lines to the next. And we can partly pick them up with our algorithm if they stay within the imaging plane. But we already suffer from degradation because the precision of the tracking in the lateral direction is between 10 and 100 times less worse actually. It's actually 10 to 100 times worse in the lateral direction than in the axial direction. What we call axial is actually direction of propagation. And the reason is actually the cell size, the resolution cell size of ultrasound, because it's very good in the axial direction, but it's not as good in the lateral direction. And dealing up with images having a very sharp profile in axial, so we can track very nicely, but it's really flat on the lateral. And if it moves a little bit, it's hard to know, especially when there's noise on top of that. So it's hard to measure. And when it comes to your observation about out-of-plane motion, then the out-of-plane is a killer, because you actually do not get the same obstacle in the field of view. And basically, the correlation between the two signals will drop and fall to very low numbers. That should warn you that something wrong is happening. If you recall, Stefan, at the presentation with the correlation map, we always look at the correlation map because it's showing how good the tracking is, and in case there is out-of-plane motion or insufficient signal or whatever is causing some uncertainty or degradation of the displacement image, we immediately see the correlation image with correlation decreasing, saying that the two signals don't look like each other anymore. And it should be a warning, don't use estimate, it's not reliable.
Okay, I propose to thank the speaker again.